We're going to look at now at a few questions dealing with tessellations. So we're going to look at exploring tessellations of polygons in these questions. First question here, which of the following regular polygons can tessellate? What you have to remember about a tessellating object is that where all of the vertices in a tessellation meet, the sum of the angles has to be no more, no less than 360 degrees. It has to be exactly 360 degrees. So what I'm going to have to do is find out of the shapes that the polygons I have here, which of my angles can add together to give me 360 degrees. When we looked at the sum of the angles in, or the measure of each interior angle in a polygon, we had a formula, M, if I turn on my pen, M is equal to 180 degrees times n minus 2 divided by n, where n is the number of angles. Okay, so what we're going to have to do is find out what the measure of each interior angle is for the four shapes we have provided here. I'm going to do a sample calculation on one of them, and then I'm just going to calculate, I guess, off screen, let's say, the rest of them. So I'm going to look at the decagon. So that's the 10-sided polygon. So the measure of the angles is 180 degrees times 10 minus 2, because n in this case is going to be 10, all divided by 10. So that's equal to 180 degrees times 8 divided by 10. So if I put that into my calculator, it tells me that the sum or the measure of each individual angle in a regular decagon is 144 degrees. Now, if I have my decagon, I have 144 degrees. I'm going to add on one other angle. I'm going to get 144. That's going to equal 288 degrees. If I add on another one, so I'm not quite at 360 yet, if I add on another decagon with another 144 degrees, I'm going to get 432 degrees. Now I've overshot 360 degrees. So when I put decagons together, I'm either going to be below 360 degrees or above 360 degrees. I'm never going to actually be able to reach 360 degrees. So that means that a regular decagon will not tessellate. Now I'm going to do those calculations for each of these other shapes. For a hexagon, a regular hexagon, each angle is 120 degrees. For a pentagon, each is going to be 108 degrees. And for an octagon, M is going to be 135 degrees. And that's using this formula right here for the measure of my angles. So for my hexagon, I'm going to add together two of them. 120 plus 120 equals 240. So I'm not quite at a 360 yet, so I'll add on another one. Well, 240 plus 120, that equals the magic number here, exactly 360 degrees. So that means that A must be the correct answer. But once again, I want to check my other ones just to make sure that that makes sense. So for a regular pentagon, I'm going to add 108 plus 108. That's going to give me 216 degrees. Now if I add on 108 more, that's going to give me 324 degrees. So I'm still less than 360. Now if I add on 108 more to that, that's going to be nowhere near 360 degrees. That's actually going to be 432 degrees, just like we saw with our decagon. So a pentagon will not be able to tessellate. How about a regular octagon? Well, I'm going to add together two of them, 135 degrees plus 135 degrees. That's going to give me 270 degrees. If I add on, that's clearly less than 360, so I add on 135 degrees more. That's going to give me, in total, 405 degrees. So once again, I've overshot 360 degrees. So when I add together octagons, I'm either going to be less than 360 or more than 360, but I'll never actually get to 360 degrees. That means a regular octagon will not be able to tessellate either. The only one that will be able to tessellate is the one where the angles added together will equal 360 degrees. So Sandra is a textile designer. She is creating a design for placemats. She wants to use a single shape to tessellate a pattern. Show how she can do this. State the measure of each interior angle in the shape you recommend. Well, there's a lot of different ways we can do this. I can start with a square or a rectangle, or any quadrilateral will do. This is my rudimentary attempt at a parallelogram. It's not the greatest. So any of these shapes will do. In a square, the interior angles are all going to be 90 degrees. In this rectangle, we're also going to see my interior angles are all 90 degrees. Now if we add up 90 plus 90 plus 90 plus 90, we're going to see 360 degrees. If you ever have a tile floor, if you see a tile floor, maybe your classroom or your kitchen or some floor has a tile floor. Often it's made up of squares, and the squares clearly do not overlap, and there's no gaps between our squares, so they do tessellate. The same is true for rectangles. Often your classrooms may be made of cinder blocks, and the cinder blocks form a tessellation. There's no there's no overlap, and there's no holes between our bricks, right? Except for, of course, the grout that holds them together. But they are essentially a tessellation. Any parallelogram can do it. My intention was to make a parallelogram with angles of 45 degrees here, and these angles here, 135 degrees. I don't know that I did the best job, but that's what we're going to see. And if we add up all the angles in a quadrilateral, we're going to see that they add up to 360 degrees. So we can repeat this shape by putting one above, one below, one to the left, one to the right, and we're going to see a tessellation forming. We can also have triangles. Any triangle will do. Doesn't matter what the angles are in that triangle. This triangle is a 90-degree triangle, but it's my intention to draw a 45, 90 triangle. So that will work. Any triangle will do. If we put 6 triangles together, they're going to add up to give you 180 degrees. The other option, besides quadrilaterals or triangles, would be to draw a regular hexagon. And I'll do my best with that one. Almost. But you get the idea. So in a regular hexagon, of course, we've checked this out many times now. The sum of each interior angle, or the measure of each interior angle, is going to be 120 degrees. So if we put 3 regular hexagons together, we're going to see a tessellation. So this would be a honeycomb shape, right? Multiple hexagons would be a honeycomb shape, like you see in beehives. So that is clearly a tessellation. Again, if we put them together, there would be no gaps, no holes, and no overlaps. So just to summarize again, a tessellation is a pattern that contains no gaps and no overlapping of shapes. We can determine whether or not a polygon tessellates if we physically tile them together. We can actually take objects and try to put them together like puzzle pieces and see if they fit without overlapping and without leaving holes. We can also determine, what we've been doing is determining whether or not a polygon tessellates when we measure the sum of the interior angles where the vertices of tiles meet. And in that case, the sum of the interior angles is always going to be 360 degrees where those vertices meet. And in that case, the polygon tessellates.